Yeah, that's sir. How are you?
Fine.
So how's lockdown going on in campus? Still same situation,
Lockdown is, yeah, here is the same situation.
but all well there, right? No active case or anything, right?
Hi. Until now, no.
Good. I think in next 4 minutes we can get started by 8:15.
Okay.
Sir, we can get started. I think some folks may be joining later.
Okay, I'm starting. Um, okay, so now we are going to start our new session. So in last, or if I say that till now, we have seen. So this is going to be the rough structure of today's talk. And what we are going to do is that we are going to start a topic which is actually called as an topic name is going to be auto encoders. These auto encoders, they are essentially important, and why they are important, we have to see it one by one and then understand that what it is and why it is important. So it's going to be that first you will see a basic recap of our fully connected network, CNN and RNN. I just have to reiterate over that so that we can understand the difference between them and really somehow figure out that what are the things that we have seen till now. And then we see that how CNNs or RNNs. In fact, here you can also have CNN or maybe have RNN, whatever. And using that, how you can use these things as a feature extractor and then use it to somehow use a fully connected network to do classification and regression. Then we are going to see something as a high to low dimension and low to high dimensional uh, projection. We'll talk about this projection. Why do we require? What is the meaning of that in one dimensional? And then we will talk about the deconvolution networks, and then it's going to be autoencoder introduction of this thing autoencoder, and then why do you require such a type of autoencoder and what are the things that you can do using these autoencoders. So before going to start about these autoencoders, I would like to first of all tell that what autoencoder can do. What an autoencoder can do, I hope that once I have explained a few things about, let me see that if I have that stuff. Yeah, so here, if you remember that few things like this. Suppose that you want to convert this image to where it is, yeah. Suppose that you wanted to convert this image to this image, or you wanted to convert a grayscale image to a colored image. That's actually image colorization. Suppose that you have got an image like this and you wanted to convert it into a denoised image. So denoising, if you wanted to do denoising images. If you wanted to, have an image in which you have given a very small region of that image and you wanted to somehow make it big as possible. So this is actually, this is called as the super resolution. And suppose that if I give you an image in which I somehow hide some part there, this part is not shown to you. If this part is not shown to you, can you make that thing? That's actually called as inpainting. So these are the few examples. If you wanted to somehow come up with a network that can do things for you. So one thing that you essentially till now have seen, that either you are doing classification or you are doing some sort of regression, you have got an image or some sort of data, and at last you are going to get maybe a single value, even such a big image, 1000 values. 100 by 100 is essentially like 10,000 values. If you have got this 10,000 values, at last I wanted to say that given this 10,000 values, you have to tell me that whether what is that, whether it's actually a cat or a dog. So only two values you wanted to know: by what probability you are saying it's a cat, and by what probability you are going to say it's a dog. That's a classification. But now just think about the problem that I am right now talking about. These are very specific, completely different type of problems. And these problems actually wanted to say, they are actually saying that that I give you an image like this, and you have to give me an image like this. So what is your input? Input is an image. Output is also an image. Now it's a completely different type of problem. I'm giving you a 10 by 10 image, 100 values. You have to give me 100 values. Previously, it was the case, I give you an image, you have to give me a bunch of numbers, maybe vector, maybe few numbers. Here also, if I give you an image like this, you have to give me image like this. If I give you an image like this, you have to give me an image like this. Or here, if I give you a black and white image, you have to give me a colored image. So if you see, they are different type of problems. And if such a different type of problems you have to somehow solve, you have to understand that your network is going to be, or your problem is actually now being converted into a picture, not say pics to pics, or if I say image to image, the correct name is actually that usually being used, that we have to use image to image translations. Now image to image translations, if you're doing, so later you will say that why only images, because you several of you may be thinking in terms of language, may be thinking in terms of some vector. So it's actually, I give you a vector, you have to give me a same dimension vector. So this type of problem, if I give you a matrix, you have to give me the same dimensional matrix. That matrix happen to be an image, then it's going to be an image to image translation. If it's a vector, then it's going to be a vector to vector translation. And this is a very, very essentially important component of deep learning. This is, by the way, going to be our first model in which we are going to train in an unsupervised manner. So if you remember that the supervised learning mean to say that I have an image and I have its corresponding ground truth. I have an image and a corresponding ground truth. Here, I am not going to have an image and a corresponding ground truth. And that is actually that it's going to be, either it is going to be supervised, unsupervised, or it's going to be a semi-supervised learning that we are going to do. So soon you are going to understand these concepts one by one. Till now, if you have any problem, then you can ask. If anyone is having any problem, then you can ask. I assume that there is no problem because I have not covered anything till now. Yes. So with this, now let us talk about that what we have seen till now, fully connected convolutional neural network. Very small recap of that, and yes. So first, small recap about whatever we have seen till now is that suppose that I have a input vector. I have got an input vector, and this input vector is actually like this. Given this input vector, this is actually my x1, in which I am having x11, x12, x13, x14, and so on, x1n, and suppose that I have got a some in between layer. So it's going to, this thing. So we usually draw it like this. That is go to here. This also go here. This also go here. This go here. This go here. This is actually fully connected. This thing will go here. 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 So if it's capital N dimension, and suppose that this is M dimension, then total weights are going to be M multiplied by N here. And then you are going to have a final output, only two outputs, whether it's a belonging to a cat or it's belonging to a dog. So it's actually being connected like this. This is connected, this is connected, this is connected, and this is connected. Similarly, things are being connected. This is actually fully connected. Here you are having M multiplied by two weights, total number of weights, M multiplied by N plus M, 2M plus the number of biases per neuron. So total number of weights is going to be m cross n plus mn plus 2m plus m, the total number of weights. Now what has happened here is that you have got a way by which you can, it's actually a matrix multiplication in which you have got an n-dimensional vector, and this n-dimensional vector is somehow being converted into a two-dimensional vector of your desired choice, and for each and every this two-dimensional vector you are having a corresponding ground truth, whether it's a 0 or 1 or it's a 1 or 0, and you solve this problem. This is a fully connected network. Then what we have seen is that these weights are going to be exponentially high. These weights are going to be exponentially very high. So in the place of these weights, what one can do is that can we share these weights? And if I can share these weights, and suppose that you are working not only on 2D, I'm sorry, not working on one dimensional data, but if you are having this two-dimensional matrices, or you can say that you are having images, and then instead of applying fully connected, we used to apply a two-dimensional filter, 2D filter, and these 2D filters are that the way we have defined is that suppose that 3x3 filters or maybe 5x5 filter, and how many such filters you are applying, depending upon that you are to get the outputs like this. These are going to be feature maps. Over that you again apply multiple layers. So we used to say that first we apply few filters and then you apply multiple more filters 3x3, and then you will again get, so these are your multiple conv layers, and at some point of time, and you do also the max pooling, and at some point of time you have got a very small feature vector, say features like 2x2. So instead of now applying a convolutional filter, we flatten it and then we apply a fully connected network. That's a CNN network for you. So you can also see this CNN network in this way, that so that we will talk about that. Right now you have got an image, and then you have got convolutional networks, and then at last you apply a fully connected network, and then at last you will get the vector classification or regression, whatever you are doing. This is your input image. Then what we have seen is that, see, the problem is that one image is not connected to the other image. Your network cannot remember that what I have seen till now. It only depends that what you are showing at the current point of time. So if you show CNN network same image again and again, I1 today, then you are going to get the corresponding output as Y1. Then you same I1, you show it next day. So t equal to 1, and then t equal to 5 days later, if you show, then again you are going to get the same Y. And at I1, and if t is equal to 100, after 100 days, if you are showing the same image, you are going to get the same Y. Now this is okay for the images, but suppose that I wanted to somehow say that I want a network, maybe some network that I don't know, and that's being said as your recurrent neural network, that if I have I1 shown at t equal to 1, then my behavior and my output is going to be, say, Y1. If I say I1 the same thing, show at t equal to 20, it is going to give me something else, that is Y2. And why you want? Because there is actually a video stream which is going to be there. There is something which is actually an audio stream that you are having, and this network should not be behaving randomly. This network should have to somehow understand that what I have seen till now, and the things which I have to predict that I am going to see, which I have to somehow classify. The information is not alone, it's actually being aggregated information, and should have to be seen not as a alone thing, but has to be seen along with the stream that what I have seen till now. And in that case, RNN started to say that I am, along with that, I am having a small amount of memory or the history, and I'm using that what I have seen till now. Depending upon that, as well as my inputs that I have got, I am going to tell you that what is going to be the output. CNN do not have that capacity. CNN just do not have any power to remember anything. And for CNN, each and every data is different, not related to each other. RNN, there is a relationship, every data that I am going to see subsequently, it's having a huge amount of relationship. And how to model that relationship? We are modeling it using a history vector, a vector in which I can store what is the most relevant information, or what are the most relevant informations that I have seen till now and may be required for me to decide the upcoming data, to decide anything about my upcoming data. Till now, we have covered that what I have covered till during this course. Now let us see that so this network can actually be CNN, or this network can even be RNN, whatever. And at some point of time, when you feel that and it depends that why you want a CNN, why you want a RNN. If there is a time series dependency, you require RNN, or the variants of RNN, otherwise you require CNNs, or the variants of different CNNs. And then we say that once you have got a feature vector, that's actually, you know, a small enough feature vector, you take and apply it the fully connected network. And at after fully connected network, you are going to get a small, you know, the final output that is going to tell you that whether what's the probability by which they belongs to a particular class, or maybe you are looking for a specific particular value, and using, I mean, you can regress over that. So this is the thing that I first wanted to cover here. If there is anyone who is having any doubt, then you can ask about this. Otherwise, we can move forward. 2 points are done. We are going to talk about the third thing. The third thing is going to be high to low and low to high. So now let us see a very interesting concept. And the interesting concept is that suppose that I have my x1, I just have shown, and my this x1 is actually having 10,000 dimensions. What does it mean? Suppose that if I have a 10 by 10 image, sorry, 100 by 100 image, I'm having a 10,000 dimensional input if I flatten it. So I take this image and completely flatten this image. I flatten and I used to get, I just have got a vector, and the dimension of this vector is actually x11, x12, x13, and you have got x1, 10,000. So you have got one such image. Similarly, in your data set, suppose that this is your data set, this is say x1, one such image, you have got another such image, you have got multiple such images, say x2, x3, and so on. You have got so many different images, and this is your complete data set. So suppose that I wanted to, given these such images, I wanted to differentiate between a cat and a dog. So what I am going to do is that I take this thing and see it as a, sorry, see it as a, you know, a vector like this. So this vector can actually be seen as x1 and a 10,000 dimensional vector. And then, you know, from 10,000, I convert it into, say, a smaller vector. And you can understand that if I make it to, say, 1,000, then total weights are here 10 power 4 and 3, 10 power 7 weights are here. And then again, I have applied another layer. And this layer is suppose that 500, and suppose that it's actually going to be a 512 things. And number of weights are going to be, say, 512 multiplied by 10 power 3, or it's 5.12 multiplied by 10 power 5. So order, you can see that's a huge amount of weights which are being there. And ultimately from 512, again, I apply another layer. And this layer is going to be, say, 128. 128. So you have 512 multiplied by 10 power 5. 5 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 multi
Sorry, I have lost voice.
Yeah, I think even I cannot hear.
Oh, looks like
I
there is
think he will be
network.
joining. Yeah.
Yeah.
Hello,
Yeah.
hello.
Yeah.
Can you listen?
Yes. Yes. Yes.
Yes, in between something has happened, so I'm going to again reshare my screen.
Sure.
Yes, now you can see my screen, right?
Yes. Yes.
Yeah. So I was showing this diagram. So was you able to see this thing, or
Mm-hmm.
this
Yeah, but
diagram?
in between, after 1,000, then we lost it. Your voice.
Okay, okay. I will again tell. So I have got a small data set in which I am having images of size 100 by 100. And for each and every image, it can be seen as a 10,000 dimensional vector. And I'm going to show my data set images to my this network one by one. And I'm having 10,000 or 5,000 images over here. And suppose that my first layer is having 10,000 things, my second layer is having 1,000 things, my third layer is having 512, then 128, and then finally in 2 dimensions. 2 dimensions are going to be whether it's actually a cat or it's actually a dog, the classification network that we wanted to train. Given this type of network, the point which you can see is that initially you have got a vector which is like this, and then you reduce this dimension. So what is happening here is that you have got a high dimensional input, and then you have somehow lowered it dimensions to some low dimensions. So from 10,000 you have gone to 1,000, and the reason behind that was that, see, in 10,000 pixels, each and every pixel is not very informative. There are so many different types of pixels, so many blank spaces, so many background pixels. They may not be anyways attributing towards any cat or dog. So instead of looking to all of them, what is the way? Is it possible that we can somehow reduce its dimension and only keep those which are the most relevant informations which are being there in my data? And if I got that, and then I subsequently keep on doing that thing, that if I can do that thing, and at last, so what you are going to do is that given a 10,000 dimensional vector, I reduced its dimension. This is actually I have. So you can see it in this way, that suppose that if I have a 10,000 dimensional space, in that 10,000 dimensional space, each and every image is actually a single point. Each and every image can be seen as a single point. And what is happening, that that these images are actually not independent images. You can say that these pixels, these 10,000 pixels, they are not independent. If I am having one pixel over here, this information is actually having some sort of relative information from this. And because of that, if this value and this value and this value, say all of them are not being generated randomly, and if they are not being generated randomly in that high dimensional space, they are not having that much amount of randomness. And essentially because of that, they can actually be moved and being lowered down into some other space. It is just like, I'm having a family of 10,000 persons, and in there I'm going to give them a 10,000 room, a big house in which there are 10,000 rooms. But these 10,000 rooms, they require? No, because they have having a close coupling, and father and son, mother and daughter, and huge amount of communities, they are going to be combined and living in the same room. They are going to share the room and share the spaces, and this is definitely going to happen in the case of images. And because of that, if I give you 10,000 space, 10,000 rooms, you are not going to acquire most of them. In fact, 10,000 things may only be requiring something like 1,000 things. And if that is the case, then most of the spaces got wasted. Now here we are not thinking in terms of compression. This can also be seen as a big amount of compression that you have done. Here right now we are not looking at the amount of compression. It is just that now you have got a vector which is actually something of lower dimension, and given this lower dimension, I will be able to will be able to process them in best possible ways. Here it's actually that 10,000 rooms. I keep on going to multiple rooms and I see that nobody is there. And here, if you go to one room, definitely you are going to get someone, because 10,000 things are actually being compressed into 1,000. So it's actually a much more enhanced and enriched representation. Why I have said it, this thing is that this can neural network is actually trying to do this thing, take things at a higher dimensional and take it to a lower dimension and keep on reducing, and the things that you are going to get in between this or other things, they are going to be much more informative than the previous things, and that is why they keep on being learning the better possible representation of the same thing. This is actually representing this data also, this is representing the same thing, and in much more lesser dimensions. So they are going to have much more useful information, which is being previously being scattered over these many things. Now it's being not scattered, it's being congested or being utilizing very less amount of space. This was high to low. But let us see another case. And suppose that if I give you a vector like this, and this vector is actually having only maybe only this, and this 4 dimensions, only 4 dimensions input. What is that 4 dimension? Tell me the state, tell me the age, tell me your if I say education, and also you can tell me your gender. I'm giving you 4 things arbitrarily chosen, and then I wanted to come up, I wanted to come up with something, some network like this. It's going in. If I say that these 4 values are going in, this is actually being asked every person. I just asked what's your state, what is your age, what is your gender, what is your education. Give it to my model, and it's going to give me what is the possibility that you are going to be affected by coronavirus, yes or no. Very random, but is it possible? Easy. You can make a very simple network. You just take these 4 values, 1 2 3 4, and then you have got a 2-dimensional yes or no, and just you add how many parameters? 4 here, 2 here, 4 to the 8 plus 2 for the biases, only 10 parameters, and you are done. You train this network. I'm giving you millions of data. What will happen? This network is not going to work. And precisely the reason behind this is that these 4 values, first of all, the reason may be that these 4 values are not relevant. They are not able to predict this thing very well. That may be the case in this example, but try to assume that I have given you the best possible 4 things and they are really related to this yes no problem. But even though this network will not be able to solve your problem because it's very small, so what you can do in such cases, when you are going to have a very small dimensional input, we used to do, that is something which is called as lower dimension to higher dimension projection. If I take and subject somehow being project into some higher dimension, this 4, I just take and convert it into a 128 dimensional vector, and then I convert it into say 4 or the two things, yes or no, in which I wanted to somehow find out. So here you are having 128 multiplied by 4, and here you are having 128 multiplied by 2. These many number of parameters that you have got. So this is actually what we have done, is that we have taken a lower dimensional input, converted into a higher dimensional input, and then I have got a corresponding output. So this is actually low to high. Low to high, if I take a lower dimension, how can I make a higher dimensional input? So the point is that from what is this? So actually, if you remember my first class, suppose that this is my data. And from this data, this is my single data, one data, only one data. I have asked 4 questions, maybe in just this case, state, age, education, and gender. 4 questions, I've got 4 output. From these 4 things, how can I make more and more vectors? Basically, these things, whatever I have got over here, these things are somehow related to my data. These things are definitely related to my data. So one way is that if I ask 128 questions over here, so I will get a 128 dimensional input over here. The other thing is that I ask 4 things and do some sort of this transformation. So what you have got over here, because you have only these 4 values. From 4 values, how you can get more and more information about this data? So it is that, suppose that I have got, this value, suppose that this value is x1, this is x2, this is x3, and this is x4. Only 4 values that I have got. My first vector can be x square, this can be x2 square, this can be x1 plus x2, this can be x1 x2, this can be x1 x2 x3, and so on, whatever. So now you can see that although I have asked only 4 questions, but essentially in principle, these things can actually be combined in so many different ways. In fact, infinite amount of different ways you can combine these 4 values so as to get the vectors or the feature that you are looking for. This is the meaning of projecting something from lower dimension to the higher dimension. If your dimensionality over which you are working, and if it is very, very small, then you will not be able to solve big problems, and several times you want to somehow convert your lower dimensional input feature vector to the higher dimensional input output feature vector, and then over that we keep on applying whatever the things that we wanted to somehow come up with the classification. If this is clear, then I'm going to talk about the third thing, and that is actually that what I have done, I have taken 4 dimensions and converted into 128 dimensions. And why I was able to do so very easily? Because I was used fully connected. Why I have used fully connected? Because all of them were actually one-dimensional vectors. If you have a one-dimensional vector, you can easily do the things. Now let us talk about another thing. If I have an image, and my image is actually of size, say, 4 by 4. Over that I apply convolution. I have got some filter. So forget about this convolution. Just you say that over that, suppose that if I apply max pooling and 2 by 2, then you are going to get this thing. And then again you apply max pooling, you are going to get 1. This is 2 round of max pooling that I have applied. From 4 by 4, I have got 2 by 2. And from 2 by 2, I have got 1 by 1. Now, this is actually max pooling. Is there a way by which I can go back? So this is, now you can see that equivalent to going from a lower dimensional space to a higher dimensional space. Previously, 4 dimensions to 128. This was actually lower to higher you was going. Here I am going from higher to lower to lower. Can I go from lower to higher? And if yes, then can I go from here to even here? Now, first of all, try to understand that what I have said. That's you are doing max pooling, and this is called as upsampling. Upsampling, this can actually being done in multiple ways, and another way is actually deconvolution, not convolution. It's actually deconvolution, and here you can also have deconvolution. So max pooling says 4 to 1. Actually, from 4 you can go to from 4 things you can make one thing. I take this, and this, and I've got one value. That's max pooling. A 4 I am converting into 1. Is there a way from which I can make 1 to 4? I've got this 1. Can I make 4 things out of that? If I have 1 like this, can I make 4 things out of that? If I have 1, can I make 4 things out of that? From this single thing, I want to make these 4 things. From this single thing, I want to make these 4 things. For this single thing, these 4 things. From this single thing, these 4 things. For this single thing, these 4 things. This is actually called as deconvolution. And deconvolution is nothing but again, deconvolution is again a convolutional function, which is being a type of convolution, and we are not going to see the details of that because it's slightly complex and we do not want to cover that thing. But upsampling is fairly easy, which says actually that if I have these 4 things over here, if I have 3, 6, 4, and 12, you have got this 12. Now this 12, how can I make these 4 things? So upsampling actually says that first I just know that what are these 12 values, how to make that, what are the 4 values out of this 12. I just replicate 12, 12, 12, and 12. You can replicate all of them, and then over that you apply a convolutional filter, because now you have got a same sized the thing that from which you have made this, you have got the same thing again back, same size again back, and over that I apply a convolution function, and you will get some other information that is going to be the upsampled version of this thing. We need to learn a filter over here such that this thing becomes as similar to this thing. This is a type of deconvolution which is being applied. But now if I say that upsampling and deconvolution, if you apply, then the way in which you was able to take an image and get its size down to this, now you have a tendency to make it again the same size. This is essentially required because the type of problem, remember the type of problem that we are going to solve. If this is a big image, this is my small, and several times this thing is actually being called as the bottle. This is several times being called as the bottleneck. Given this bottleneck, we wanted to make, so here you make slightly bigger than this. So here this thing and this size may be same, and then you make something over here, and what you are doing deconvolutions. So first you take this big image, make it a smaller image, make it another smaller image or the features, and then from this you have made this, from this you have made this, and from that you have made another thing, and with that you have made the final thing. So what is happening over here? Here you are doing max pooling, here you are doing deconvolutions and upsamplings. So if you do deconvolution, from 1 you can make 4 things. In fact, from a small image you can make, or the small feature, you can make bigger images and bigger features, the things that you are actually interested in. Why? Because now we are going to train image to image I have an image, I want an image. Is this
So,
okay to everyone? Yes.
yeah, Aditya, Raish here. So, is these conventional methods will be used for mainly on images or even any other data sets also? Like, let's say I have four data inputs, and I want to make that as combination of small size or smaller numbers, and even from smaller numbers to again like higher numbers. I think.
Yes. So any type of data you can apply. The only thing is that if it's a image or if it's a 2D type of data, then you need to apply 2D filters. If it's a 1D type of data, then you need to apply 1D filters or need to apply the fully connected. That is
Okay.
the
Okay.
any type of data you can apply. If they are images, then usually we apply CNNs. That's why I just have shown here that it's actually not an image data. This thing is not an image data. This thing is actually my 4 values. Given this value, I have converted into a bigger value. And why deconvolution is not applied? Because even from going from here to here, I'm only doing fully connections, fully convolution. Sorry, fully connected network. It is not even convolution. So that's why we do not require deconvolutions. But if you have, in this case, you can see that how I'm going to reduce the size of my images. I'm going to reduce the size of my images by applying max pooling. So the reverse of that is actually deconvolutions and the upsamplings.
Got it. Got it.
Got it. Okay, good. So once we understand this, okay, now we are going towards the topic, today's topic. So with this, I guess that whatever the things which are required, I have covered. Now we are going to the core topic, the thing that I'm interested to talk about. And let us talk about that. I have a cat image, one cat image fixed, one cat image, fixed cat image, and assume that this cat is actually being something like this, placed over here. This is my cat. And I take this image and and I have somehow what I have done is that I take a vector and what I have done is that I have taken a vector, and this vector, suppose that I am having this vector as of size 1024 dimensional vector, and all of them are actually one. All of them are 1, 1, 1, 1, 1, and 1. Fixed. This image is fixed. All of them are 1. And then I made a bigger vector. Then I made another bigger vector. And sorry, this is not a good thing. And at last, I have made a exact image. This here, so what is happening over here? Here we are doing deconvolutions. And the image size is right now, say 100 by 100. And at last, I made a network in such a way so that at last I will get 100 by 100 as an output image. Suppose that this is 1024. Over that, I am applying certain things. So this is actually a this 1024 thing, and over that somehow I first of all make it slightly bigger, and maybe from 1024 I have got converted to directly 10,000 things, and then given that 10,000, maybe not 10,000 over here, let me make this network a small network for you. Maybe then I make it 5,000, then I make it 8,000, and then I make it 10,000. But instead of making this 10,000 in this single vector form, I reshape it and make it a two-dimensional matrix for me. This is my two-dimensional matrix. This network is clear, I assume. I have got an image. This is a fixed cat image, 100 by 100 size. I have fixed a vector, 1024 dimensional vector, and all these values are set to 1, 1, 1, 1, 1, 1. And here how many weights I have got? Here I have got something like 5 into 10 power 6 weights. Here I'm having 5 at 4, 4 multiplied by 10 power 336 plus 7 weights. Huge amount of weights are there, by the way, that's okay. And then at last also have got huge number of weights. And given this network, assume that this is my network and I am drawing it in this way right now. Now you can see that what is the meaning of this, that I have a small thing over here and I make a big thing over here. So it is actually low dimension. I have made a high dimensional output, and this high dimensional output is actually an image. I reshaped into an image. So you have got an image. Your input was all ones, and you have got a cat image. This was actually your fixed cat image. So suppose that this is my I1. I am going to get I hat as an output, and my loss function is going to be I hat minus I1. This is my loss function. So if I train my network that when I am every time going to show you all ones, every time I keep on showing you all ones, fine. You have to make an image for me, fine. Once you make an image, I find out that how close, whatever you have made, how close is that image to my cat. Find out this, find out the loss, and back propagate. And then you again take 1, 1, 1, 1, 1. Fixed. Same input is again being shown. Again, this whole thing happen, forward pass. You again will get a loss, and again you back propagate. What you wanted to train? You wanted to train your network that whenever I show you all ones, you have to make this cat. Whenever I show you all ones, you have to make this cat. If I give you something else, I don't know what you are going to make. But if I give you all ones, you have to make a cat for me. This is something amazing has happened. If you see, cat is not even shown directly to my network. You have not even shown this cat directly to my network. It's not being even shown, but still my network is able to make the cat at some point of time, because this is my loss, and this loss is keep on going low and low. As soon as it become very small, what will happen after once this network is converged? What will happen? You show 1, 1, 1, and it is going to make a cat image for me. But this cat is not being shown to my network explicitly at a single time. It's only whatever I have seen. You make, I check, and you back propagate. You make, I check, and you only back propagate. You are not being shown this thing directly. Still, once this network is trained, it is able to make this cat that it actually have not seen at all. This is a way by which you can say this thing in this way, that the weights which are being there in my network, these weights actually somehow saved this image, and this image actually got saved inside my network. I have saved one image in my network, and it actually understands that when all ones are being given, I am going to give that image back. All ones, I will give the same image back. It's actually like key. This is actually the key. All ones are actually the key for this image. I can save one image in this way. Now let us talk about, I have another image. Suppose that is a dog image, some dog image. And then I say that for this, I have another key. I have some separate key for this, which is say all zeros. And then I take and do the same thing. I sometimes give 1 1 1 1 1 and make cat find out the loss with this image. Then sometimes I give this 0 0 0, whatever you make, I find out the loss with this. In this way, my loss keep on decreasing. Once it got decreased completely, if I give 1 1 1 1 1, it will make this image. If I give 0 0 0 0, it will make this. Now see that network has not even seen this, not even seen this. In fact, the whole database, if you have huge amount of images in your database, giving these values differently, you can keep on storing these images inside your network. What you can say is that you can use your neural network, as a data set, as a data structure. Your neural network is actually behaving as a data structure, which is saving all of your images inside your network and keep on giving you different images whenever you want, depending upon your inputs. They are actually serving as your key. Now the point is, suppose that if I have 10,000 different images or 50,000 images in my data set, 50,000, 50K images, how you are going to decide that which image is going to have which key? If there are two, you say that all 0, all 1. If I say, if I say that you have 10,000, if it's actually a 10-dimensional input, 10-dimensional vector, then only 10 images you can code. Each and every image can be used as a one-hot encoding. So first image encoding can be first image encoding can be 1 0 and so on. Second is 0 1 and so on. Third is 0 0 1 and so on. So in this way you can also say that it can be one-hot encoded. But suppose that if I say that no, in this way I'm going to waste, let us do it in this way, that if there are actually 10 dimensions, first is 0 0.5, 0 0.2, 0 0.6 and so on, and then the second for my second I2 image, my vector is 0. Or my key is 0 0.3, 0 0.6. Now it becomes very tedious. But if you can do that, you can save memory. But how can you do it for huge amount of images? There are 50K images. Manually you cannot do. So this is my network number 1, and that I used to say as the decoder. Why it is decoder? I am giving you I'm giving you a vector and you are decoding me. You are decoding that what is shown or what is hidden inside this vector. That's why I'm saying that it's actually being set as a decoder. I give you all 1, you will give me a cat. I give you all 0, you are going to give me a dog. That's why we used to call it a decoder. This is one network. But now suppose that if I have 50K such things, how can you give each and every image in your data set a unique number like this? It becomes a tedious task. So I intelligently have done what is that I take this whole data set, all 50K images, and train another network. I train another network, this network, and this will take images as an input and give me the encoding as an output. I give the images, I take an image over here, show it to my network, and I'm going to get an encoding. How many? That whatever the 10 dimension or 128 dimensions or whatever the dimension which is required by your decoder. And I say that this is actually encoder. Why? Because this is actually saying, so instead of doing it on my own, I have designed a network, I have devised a network and said that, oh, you have to give me the encoding. I give you the image, you have to give me the encoding, and I take this encoding and show it to my decoder. And you are going to get an I dash. So let us draw it in the complete form. So this is like this is called as my decoder. This is my input I. This is my encoder. And this encoder I have got, and I have shown it as a bottleneck or the embedding or the input feature vector for my decoder. And then I again apply a decoder over that, and you are going to get a I hat, and you are training it as I minus I hat and training like this. Let us ask any question at this point of time. If there is no question, let me carry forward. I have got I have got I hat, I have got I minus I hat. This is my loss. What is the meaning of this network? This will take I, give me an encoding. Decoder will take that encoding, convert it into I hat in such a way so that this thing has to be as close as possible to this. That is why this is called as, first of all, auto encoder. What you have got here is actually the encoding. Encoding of whom? Encoding of I. That is why it's encoding itself. It's encoding itself, and by the way, this thing is going to be a big number and this thing is going to be a small number. That is why it's actually a small encoding. This may be say 1000 by 1000 image. This may be say 10 by 10 or 15 by 15 or 30 by 30, very small number. That's why from this you have got an encoding, and see that from this simple encoding, if you are able to make this full image, which essentially mean that, and if your network is trained in good possible way, from I you can make I hat, from I you can make I hat, but from I you are not making I hat, from I you are making this small thing, and I hat is just being made by a small thing, which mean that whatever the things which are being there, most important, relevant and significant things are being saved over here, because your decoder is able to reconstruct the same input via this small amount of information that you are going to give to your decoder. First thing is that is why it's called as auto encoders. Second thing is that this is actually taking a embedding or encoding, converting into the image. This is taking an image, converted into a embedding, and together when you join, they are actually two set of network. Now we are going to talk about two networks. Till now we are talking about only one network. I am talking about now two networks, encoder and decoder combined together. This is called as auto encoders. How it's being trained? You just have to take this loss. This loss is actually the MSE or RMSE. MSE is actually the mean square error. There's a root mean square error you can do, or the mean square error you can do. The simple error between the two things that I have got, how far and how close they are. You can train your network in this way. I assume that this is again okay to everyone. Now let us go and talk about another thing, that what is the next thing? Yes, so why do we require? So now let us go and talk about, once we understand this, you can see that this is our first generative model. What is the meaning of generative? What is the meaning of unsupervised? See, the meaning of, first of all, the unsupervised training, that you have got an I. From this I, you are making I hat. You do not know that what is this I, but still you can train your network with this type of loss. Why? Because you have I, you have got I hat. You just have to, need not to know that whether it's a cat or a dog or this or that. No class specification. You just have an image. You constructed an image. You need not to worry about the label of this, but have to reconstruct and find out the loss and back propagate. That is why it is unsupervised. Is there any doubt about unsupervision? No. No doubt about unsupervision. So let us talk about generative model. Generative model and discriminative, there are two different types, two models which are available. First one is This,
Aditya sir, I have one question. What is a
please
loss? I
answer.
mean, yeah.
Yes, yes. Let me, okay, thank you. Let me clear it. So the loss here is going to be that if I have got an image of size 2 by 2, say I, and I have got my I hat as this. Now suppose that this is I11, I12, I21, and I22. And suppose this is I hat 11, I hat 12, I hat 21, I hat 22. The loss between them, or if I say I minus I hat and this thing, it's actually pixel by pixel loss, which is just the summation of I, or if I just write it to as addition, I11 minus I11 hat square plus I12 minus I12 hat square, and so on, and then add all of them, and that is the meaning of this loss, and this is also called as the MSE, mean squared error. Is this okay?
Okay.
You can further ask, please, any clarification. You can ask your question.
Aditya sir, what I'm advising that if I'm a decoding, so
Yes.
same image I'm a decoding, right? So
Yes.
where it getting lost? Because if I'm going in general concept of encoding and decoding, it gives
Yes.
me just a different structure of decoding value, right? So,
Yes.
but here we talked about the loss. So I'm not correlating where we are losing this loss. I mean, because
Yes.
same image I am decoding, right?
Yes. Let me answer it in this way, that why you are able to why you are first of all getting lost is that you have taken this image, converted into a very small compressed form, and from that compressed form you are making the whole image, not from this whole thing. This is actually having all information. When you take all of this information, compresses into a very small encoding or the bottleneck, your decoder is not able to see whatever is being here. It's only able to see things over here. Only this thing. Only from this, if you are going to make this thing, you will not be able to make maybe the exactly same information again back. That is why you are going to get some loss.
Now I got it. Yes.
Okay, fine. Any other question if you have? No questions?
No, sir.
No. Okay, so this is done. Loss was okay. Generative, I was talking about generative and discriminative models, and these two models were actually discriminative and generative. Now let us talk about for some time to understand, because from this is actually our first generative model. After that, we may be after this we will be talking about variational autoencoder. That is also a generative model. Then we will be talking about GANs, generative adversarial model. So all these models now we are going to read, they are going to be slightly different from the discriminative model. What is the difference between the discriminative and the generative models? So what these models are going to learn, they are going to learn some specific type of task. One task is discrimination, other task is generation. What is the difference between both of these tasks? If I show you, if I say that I am going to show you multiple images of one, you just have to say that whether it is one or it is not. This is a discriminative task. If I say that I am going to show you multiple ones, and at the end of your training, you have to write one, you have to generate one in your copy. Now, these are two different tasks. First is only understanding how to differentiate between one and the things which are not one. All different types of one, you are showing your network one by one, and your network has to understand that what one looks like, and in fact what ones look like, probably it may learn, it may not learn, but at least it will learn that how the features of one
are discriminative, and discriminative then remaining things. But in the case of generative models, one should have to really understand that how to write one, how to generate one. So if I say that generative network is going to learn generative features, generative network is going to learn the generative features, discriminative network is going to learn a discriminative features. Both of them are actually two different types of feature. If you have a small kid, you show it 1,000 times 1 and then 0, and then at some point of time when you feel that this kid is able to understand this is 1 and this is 0, then show it. Or 1 and 0 is a simple example. You just say that A and B, and you say that this is A and this is B. At some point of time, after seeing 500 images, the small kid, maybe in the first class or the second class, will be able to understand that, okay, this is A and this is B. Now you give him a pen and say that write A. He will not be able to write A, or may write but may not be perfectly able to write A. The way in which it is able to discriminate. Why? Because it's not being trained for this. Because it only had learned the discriminative features. If you have trained, and just remember that when you train your kid, write 1, then he write all different types of 1 except the actual way in which A or 1 has to be written. And then you keep on training. No, the line is not like this, the line is not like this. He will write A like this. Then no, A has to be like this. And oh, okay, like this. This is my A. And then you keep on training it. At some point of time, then no, A has to be something like this. And then he started to write that, okay, he's saying that it may be an A. Then it got trained and say that it may be an A. And slowly it started to understand. Now that is the difference between training and training something to generate, and the training something to discriminate. Now you see that this network is somehow understanding. I give you an image, you have to make an image. This is the first generative model. It is taking an image, generating an image, and that is why it has to learn the generative features. And I assume that we all can agree that several times, in most of the cases, generation is much more difficult than discrimination. If discrimination is easy, several times, it may not be every time. Sometimes it may be the case that you want to differentiate between two things which are very similar, but it is easy to draw them. So, but most of the time, getting the best possible generative feature, your network has to learn in a much more balanced way. It's slightly more complex work than understanding how to discriminate. So discrimination we learned, and discrimination is actually being learned using different types of classification networks that we have seen till now. Now for the generative cases, we have to understand how to train a network to understand the generative features. With these generative features, what we need to do is that so as I have said that this is my first generative model, you all agreed that yes, I have got I, and from that I am generating I hat. Maybe some amount of degradation from I may happen, but more or less very similar type of images you are going to generate. So you are able to generate new images. Yes, but is it really new? And you have your own data set. In that data set, you have got an image. You show it to your network. You have got I hat. This is very similar to the image. So what you have generated? From the same image, you are able to generate the same image. And what's the reason? The reason is that your decoder is able to generate new things. Fine. Your decoder is able to generate new things. But for decoder, you require an input. And who is going to give you the input? To get this input to your decoder, you require the original image to be shown to your encoder so as to get that input. So this is actually the problem which is happening over here, that although you are able to generate new images, although your decoder is able to generate images for you, but these images are no different or exactly similar to the images that you have in your data set. And if you have that image in your data set, then there is no reason to generate that image from your decoder or encoder network. Your decoder is able to generate, fine, but to generate, it requires to generate something, it requires a feature vector. It requires a embedding, and to get that embedding, you require the original image to be shown to your encoder so as to get that thing. Now this is a chicken egg type of problem, and because of that, what is happening that you are not able to generate really new things. You are only generating some things which are being already there in your data set, and if that is the case, then it's not a real generation. You are not able to generate anything, and autoencoders are actually of no use at all. First of all, if your autoencoders are of no use, then why we are doing this thing? So today, in next few minutes, we are going to talk about two simple applications of autoencoder, and then we will see much more complex applications of our autoencoder. First thing is that I can generate new images, but how I can generate is that I will take a image, I show it to my network, get an output. From here, the bottleneck, from bottleneck I have got an output, say I dash, and I randomly perturb. So I have got a vector. I slightly modify this vector, very slightly modify this vector, and then show it to my decoder. You are going to get another I hat, and this time this I hat will not be exactly same as the image that is there in my data set. Suppose that this is a cat image. You are going to get this vector for this cat image. I take this vector, I take this image cat, show it to my network, got a very a vector. I slightly modify that vector, show it to my decoder, not showing the exact vector but a slight variation of that vector. You are going to get another image which is very similar to my cat, but may be completely different. Maybe the color of the cat may be different, maybe the size of the cat may be different, maybe the location, maybe certain things are going to be changed. And in this way, you can generate small amount of variation in your data set. So previously it was having 50,000 images. After this type of transformation via this network, you may generate 50 more thousand images out of your data set. So you have slightly got more images than the previous image set of images that you have. Generation happens. But this was one thing. The second interesting application, and I can tell you that several times we used to do this type of application, is that I have a, just see, I'm having a network like this, and this is my CNN network. I take, and then I have a classification. We all have seen this thing. So this is my classifier. This classification is happening over here, and at final layer I have got a output vector which is going to tell that the image that you have going to show to my network I, what is the probability by which it belongs to different classes. Here, this image is shown to my CNN. I have got some set of features that's being shown to my fully connected network. We used to call this network as, this fully connected network, we used to call it as classification network, and then we have got this classification vector. Okay, now let us see that instead of training it in this way, if I train this network in another way, the another way is that forget about whatever is being shown in between. I have got a network like this. So this is actually a complete autoencoder. I have, so instead of seeing it as a CNN feature extractor, you see it as encoder, and you make a compatible decoder here. Instead of forget about whatever I have shown in between, you see it as a complete decoder we just have talked about. This is my decoder network, and I train this. I train my CNN, this CNN network, so as to get my best possible decoder network. And decoder network, so you generate an image, so you show image I and show it to and make this network in such a way so that whatever the features that you are going to get over here from this image, you show this image, you got some features, you make that these features should be in such a way so that my decoder is able to generate the whole thing, the same thing again from this small number of features that I have. With this small number of features, if I can make this image again, this means that it has actually encoded well. It has encoded well this image, because instead of using this image, my network, my decoder is able to generate the exact image from this amount of information, which is very less than the actual information, which essentially means that I have got the best possible or a good set of features over here. Once you train this network in this way, what we are going to do? We are going to remove this network, by the way, and only train. So our this network got trained. Then I remove this network, and since this network is trained, I add this network again, and then only train this network. Freeze it. I don't change this network. This network is actually being trained via this network. Once it's been trained, I freeze it and only and remove that network. I have removed this network. Instead of that network, I have applied or added this network and trained this network. Why? Because this I have got a very good set of features. These features are actually generative features, and usually generative features are much more enhanced and richer than discriminative features. So this network somehow is getting good set of features over here. These are my generative features. First I train this network, keeping it fixed. After some amount of time, when this network started to perform well, I keep on changing this thing as well. So now my losses start from here and only be back propagated only up to this. Later, once it's actually got good amount of performance, then I keep on back propagating at the last, from back to the end or end to the first. Why I'm doing that is that from here I just take my loss and keep on back propagating to my first layer, because now I wanted to slightly convert or change my generative feature slowly towards my discriminative, because ultimately this is doing discrimination. Here you are getting your best possible features. You wanted to tweak and adjust your best possible feature in the way so that it can complement my classification function. So what I have said is actually a very good way of pre-training your images. You pre-training your this network, because if you have 50,000 images, you show this network one by one and have a decoder network connected to it. So this image got shown to my network. I have got some image, find out the loss like this and the difference between this. And in this way, 50,000 images are there in your data set. It's an unsupervised learning. You just need to take any image, show it to your data and see that given that image, my bottleneck is able to make my actual image back, and training your CNN encoder in such a way so that it's able to encode itself in the best possible way. So this image got best possible way encoded here. Then you stop and remove this second network, add classification network, and keep on training this classification with this best possible feature for some amount of time. Once it got trained, you keep on back propagating to back, and you are actually training the classification model in the better possible way. It has actually been seen that if you train your network in this way, several times your performance slightly got enhanced. In fact, several times your network also performs or converges fast. Yes. So this was the thing that I was trying to figure out today, And in the next lecture, we are going to talk about few more applications of few more interesting and slightly complex applications of autoencoders, and then we will go into the variational autoencoders. Any questions? Then I can answer, or we are done. I am done.
No, sir.
I
We'll
hope.
go through one more time. Yeah.
Yes. So please go, and in next class again, first I will take few questions and any doubt, slight amount of recap, and then do the application related applications, and then we will go into the so variational autoencoder. It's a slightly complex topic, so that is why it requires some building of stuff. So we'll keep on starting that thing in next lecture.
Sure. Sure.
Okay.
Yeah.
Soon you are going to have your lab as well in autoencoders and then variational autoencoders.
Yeah, that will be more clear. Yeah.
Yes. Okay. Then.
Yeah.
I see you.
Thank you, sir.
Thank you. Thank you.
Okay. Thank you. Bye bye. See you.
See you, sir.
Okay. Bye.